Hello everyone. Today I'm gonna cover the last two sections of chapter 14, section 14.7 and section 14.8. They are talking about finding the maximum or minimum values of a given function. Okay, so let's start with section 14.7. So in this section, the main problem that you guys gotta face is this: given a function, say two variables, z equal to f x y, and whatever it is. Okay, they're gonna ask you to find the maximum or minimum values of that function. So in this section, you guys are gonna see two types of maximum and minimum. You can have absolute maximum or local maximum. Same thing for minimum. You may have the absolute minimum or local minimum. And I claim that this section is very similar to the one variable function that you guys learned in Cal 1 about finding the maximum or minimum. So I think it's a good chance to recall Cal 1. Recall one variable function, y equal to fx. Okay, say I give you the graph. And you want to find local maximum or local minimum. The first step that you guys did was what? You take the derivative, say f prime of x, and you set the derivative equal to 0. You solve for x. You have something called critical value, right? Critical value or critical points. Okay, those are gonna be your candidates for local max or local mean of the function. Okay, and then you take the second derivative. I think it's in Cal 1 it goes what the first derivative test and then the second derivative test. Take the second derivative, you set it equal to 0, you solve x. Or again, that point gonna be the point of inflection or inflection points. Point of inflection. And then if f double prime is positive, the function is concave up. F double prime is negative, the function is concave down. So by the way, in the graph, this point right here is going to be your local maximum. The point right here will be your local minimum. Okay, and the point changing from concavity. This is concave down, concave up. So this is a review. So I'm going kind of fast. Okay, this is the point of inflection. This is local max. This point is local mean. This point right here is a point of inflection. Okay. So for the first derivative test and the second derivative test, going to help you to find local max, local mean, and point of inflection. Okay, that's about local max, local mean. Now, if you have a problem that asks you to find the absolute max and absolute mean as well, so after all the work you do right here, you have to find the endpoints. Okay, so usually in this type of problem, the domain or the interval that they apply for the function is gonna be closed interval. So they have endpoints. So if the function go down forever, go up forever, you will not have local max or local mean. But if they stop like this, then this will be your absolute minimum because it is the lowest point on the graph, and that is the absolute maximum. But if the graph is like this, you start right here, stand right there, and this is still your absolute max, but this is not the absolute minimum anymore because it's not the lowest point on the graph. This one gonna be the local mean, and at the same time it will be your absolute mean. So in a nutshell, after finding all the local and you want to find the absolute max or mean, you have to test for the endpoints of the graph. Okay, and then you take the lowest point on the entire graph for the absolute minimum. You take the highest point of the largest value on the entire function for the absolute maximum. Okay, and the idea gonna carry over to Cal 3. However, it's gonna be a little bit more complicated because you guys don't work with one variable value function anymore. This time, multivariable. It's gonna be 2 or 3. This section 14.7, we're gonna deal with 2 variable function. Okay, so you have something like z equal to fxy, and this is the step that you guys gonna follow. Very similar. you have fxy, right? Now you don't take derivative. Instead, you're going to take partial derivative. So you take fx, okay? And then you calculate fy, right? Fx means partial derivative respect to x. Fy means partial derivative respect to y. And then you set fx equal to 0, you set fy equal to 0, and you're going to have a system of equation. Then you're going to solve for x and y. Guess what? Those points will be your possible local max or local mean, or maybe neither. But if you're looking for local max or local mean, those solutions for the system equation right here will be good candidates. All right, and after taking first derivative, you have some points, some values, critical points, critical values, just like before. Critical points. Okay. Could be local max, could be local mean, but you don't know whether it's local max or local mean. So we're going to move on to something called the second derivative test, right? So partial derivative to be precise for a multivariable function. So you're going to calculate what? F, x, x. You want to calculate f, y, y. And then what? F, x, y. And then f, y, x. F, x, x means what? Derivative, first derivative of x, and then take the derivative one more time with respect to x again. Fyy means what? You take a partial derivative respect to y, right? And then you take the derivative respect to y one more time. Fxy means fx, and then derivative in terms of y. Fyx means fy, and then take the derivative in terms of x. Okay? And then set them all equal to 0. However, the last two right here, and I glance it's going to be the same because the function is continuous and differentiable. So fxy is going to be the same as fyx. So technically, you don't need to do all four because the last two are going to be the same by a theorem called the Claude theorem, as we have before. Set this equal to 0, this equal to 0. Let me see. No. We don't set it equal to 0, I'm sorry. We have those three. So we're going to calculate something called this. D. I think D stands for determinant. D is this. Fxx times fyy minus fxy squared. Fxx, fyy minus fxy times fyx, but it's the same, so xy squared. Okay? You have a value for D. And you have several cases to look at. If D is a positive number and fxx is a positive number, and the type of the graph is going to be like this. Okay? This one going to be concave down, so this one going to be minimum, local minimum. You have a local minimum. But if D is positive, but fxx is a negative number, it's going to be upside down, so you're going to have a local maximum. Right? If the determinant D is a negative number, then the point is like the point of inflection. But in multivariable function, we call it the saddle point. Saddle point. Okay? So it's not a local max, a local mean. Alright? And if somehow you're not so lucky, you calculate D and D is neither positive or negative, in other words, if D is equal to 0, and you have no clue, inconclusive. Okay? So you cannot tell whether the point is a local max or local mean or a saddle point. This is how you take care of a Calc 3 problem. And this is the main idea for 14.7 for local max and local mean. And of course, the next step, they ask you to find the absolute max, absolute mean. Usually, in the question, they're going to keep you in a closed domain, a closed dish. That's how they call it. You have to look at the boundary. And I think it's better if I give you the example for those, and you guys are going to see it a little bit better. So let's start the example. This is the main items that you guys are going to look at, the main step that you're going to see in 14.7. So let's start with the example. Okay? let me just use the example on the book so you guys can read them for your reference. Okay, example. Looking at example. See, example. We have f x y equal to x to the 4 plus y to the 4 minus 4xy plus 1. X to the 4 plus y to the 4 minus 4xy plus 1. And in this question, they only ask you to find the local maximum or local minimum. They didn't ask you for the absolute, which is good for us. We don't have to do a lot of work, right? Less work, right? Just local max and local min. X to the 4y to the 4, 4xy plus 1. Okay, so we start. And by the way, the domain of this thing is what? All real numbers from negative infinity to positive infinity. So all over the xy plane, all right? So we start with fx. By the way, fx, x comma y, this is how we write it in full. But eventually we get lazy, so we kind of omit the x comma y if we understood what it is. It's equal to what? 4x cubed. We take the derivative with respect to x. Okay? And this is 0. This is minus 4y. And then you calculate fy. That's x comma y. This is 0. This is 4y minus, this is what? 4x. Derivative constant is 0. Okay? You got the first derivative, partial derivatives, and now you set the partial derivative equal to 0. And then you guys try to solve x and y. So from the first equation, I got x divide both sides by 4. Okay? So I got x cubed minus y equal to 0, or y equal to x cubed. And similarly, this is cubed. We got that. Okay, and for the second equation, I got x equal to y cubed. I don't think I need the second one. I got x equal to y equal to x cubed. All right, so I'm gonna plug into the first one. I got the first one plus to the second one. Second one is what? Y cubed minus x equal to 0. Okay, so y is x cubed, so y cubed is x cubed minus x equal to 0, and y is x cubed, right? Y is x cubed. This is the second equation. Y cubed minus x equal to 0, and y is x cubed, so y cubed is x cubed cubed. This means what? X to the 9 minus x equal to 0. Now you have to solve x from here. This is a polynomial, very high degree 9. I can factor the x out. So I got what? X to the 8 minus 1 equal to 0. Now I see that I can actually factor this out more. I'm going to use in this very popular identity. The difference of the square. X squared minus y squared is equal to x minus y times x plus y. I'm going to think of x to the 8 as x to the 4 squared. So this is x times x to the 4 minus 1 times x to the 4 plus 1 equal to 0. Okay? Because I think of x to the 8, x to the 4 squared. And of course, 1 is 1 squared. Now I see this is x to the 4 plus 1, the positive value, if x is real. And then x to the 4 minus 1, apply the same strategy. I can factor out again. So it's going to be x to the 4 is x squared minus 1 times x squared plus 1, and then times x to the 4 plus 1 equal to 0. Do it one more time for x squared minus 1. X times x minus 1, x plus 1, x squared plus 1, and x to the 4 plus 1 equal to 0. Well, x squared plus 1 and x to the 4 plus 1 are all positives already. So if the product of 1, 2, 3, 4, 5 factors is equal to 0, either one of those 3 factors is going to be equal to 0. It means what? X will be equal to 0, x will be equal to 1, or x equal to negative 1. Okay? And then you can solve for y. From here, y equal to x cubed, x equal to 0, and y is 0 cubed, 0. X equal to 1, and y is 1, x is negative 1, and y is negative 1 cubed, it's still negative 1. So you have 3 critical points, 0, 0, 1, 1, and negative 1, negative 1. They could be local max, they could be local mean, it could be saddle point, or maybe neither. Who knows? We have to test. Okay, so we have used the first derivative, partial derivative, and we found 3 critical points. Now let's move on. I'm going to do the second derivative. Okay, this is my first derivative function. So I'm going to calculate f(x)(x). Fx right here, fxx is going to be 12x squared. It's all y, so f derivative of x is 0. Okay, now calculate fyy. Fy right here, fyy going to be 12y squared. And then we're going to calculate fxy. Fx right here, the derivative of y is going to be negative 4. And you can calculate fyx if you want to. Fy right here, the derivative of x is going to be negative 4 as well. So I told you, the last two are going to be the same. So technically you don't have to calculate them both, just one is good enough. Okay, and then you're going to calculate d. D is fxx times fyy minus fxy squared. And by the way, this is for the side work, okay? People usually think of it as determinant of the matrix. Think of it as fx, x, fxy, fyx, fyy, and then determinant is what? Fxx times fyy subtract fxy times fyx, okay? And that's going to be zero. That's how they call it D, I think. Okay, so calculate this one. Fxx is 12x squared. Fyy is 12y squared. And then fxy is negative 4. So negative 4 squared. So simplify this is 12 times 12 is 144. X squared, y squared minus 16. Okay, now see if this one is positive or negative. First, I'm going to plug in x equals 0, y equals 0. I got a point right here, the first point that I'm going to test. Okay, try 0, 0, then d is what? 0 for x, 0 for y, so d is equal to negative 16. It is a negative number. And I'm going to try fxx at 0, 0. Fxx is right here, is equal to 0. Right? Because x is 0. Oh, but d is negative already. I don't even need to calculate fxx because according to what we learned, if the determinant d is negative, and what? This point going to be the saddle point. Saddle point, for sure. Okay? Doesn't matter if x is positive or negative. Now try the second point. 1, 1. What do I have in plugging 1, 1 in here? It's d is 144 minus 16, which is 128 positive. Now it's going to be a local max, a local mean. I'll plug in fxx at 1, 1. Fxx 1, 1 is what? 12. Right? Positive. D positive, fxx positive. Graph like this. That's what? Local mean. Okay. Similarly, you try negative 1, negative 1. Now I need some room to write, so let me erase this. D gonna be the same because x squared, y squared, so still 144 minus 16, so still 128, still positive. And then fxx of negative 1, negative 1. Look at negative 1 in here for f. We don't have y, don't worry about it, still 12. Still positive, so you have another local minimum. So both cases going to give you local minimums. So in this particular problem, you don't have any local maximum. Instead, you have one saddle point and 2 local minimum. Now, question may ask you a little bit more. They ask you to find the minimum value, the local minimum value, and that is very simple. You know 2 local minimums, right? You just plug the point back into the original function. you'll find the minimum value. But try it. At 1, 1, and F11 is 1 plus 1 minus 4 plus 1, so it's still -1. And F -1, you do the same thing. Look at -1 here, I still have 1 plus 1 minus -1 times -1 times -4 is still -4, and then still plus 1 equal to -1. So you guys have two local minimum, and the minimum values is -1. Okay? So I haven't grabbed this one yet, but after having the values, I guess the graph is kind of like this. Not sure, but it looks like this. Okay? And the graph is kind of like this. Okay? You imagine that it's like the bottom. Okay, the bottom of the bottom. Okay, like a water bottom. It looks like this. And this is a local minimum. This is another local minimum. Okay? And this is the saddle point that we're talking about. Okay. It's not the MAC because it's going to have some point around this. It's going to be higher. Just like that. Yeah. And this is the first example. And hopefully via the first example, you're going to see the step that we are following to get to the answer. So I claim that with this section, 14.7, you do have a recipe, a formula to apply to find the maximum mean. First of all, first derivative, first partial derivative, set them equal to 0. Find the critical points or critical values. It's going to be your potential local max or local mean. And then you find second derivative, calculate d. Okay, if d is negative, set a point. D is positive, depends on fxx. Or if you don't want to calculate fxx, you can do fyy, because x and y play the same role in the game. So d positive, fxx positive, you have a local mean. D positive, fxx negative, you have a local max. If d equal to 0, inconclusive, you don't know. Okay? And then you have the points. Now I'm going to move on. I'm going to give you another example. This time, I'm looking for the example that asks you to find absolute max and absolute mean, right? So you have to find the local max, local mean, and then look at the boundary of the function. Okay, let's take a look at one more. Let me just use the example in the book so you guys can look it up when you want to read the book by yourself. Another one where it's absolute. Oh, right here. Fxy equal to x squared minus 2xy plus 2y. X squared minus 2xy plus 2y. Yeah, and now they give you the condition for x and y. X is somewhere between 0 and 3, and y is somewhere between 0 and 2. Okay, so before solving this, let me try to sketch a graph. I don't know the graph yet, but just roughly, okay? Okay, this is my z-axis, y-axis, and x-axis. X here, y here, z here. And say you have a graph. Okay, so this is the surface. This is fxy. This is fxy. Okay. And x run from 0 to 3. 0 to 3. Y from 0 to 2. Okay. So we are not looking at the entire surface right here. We only look at the surface that right on top of this rectangular region right here. So in other words, this comes kind of somewhere here. Okay. Portion of the entire function right above this rectangular region. Okay. These two more. more complicated to project it down. Okay? And by the way, then equal sign is included in the equality. So this region right here is called the closed region, including the boundary. So after finding local max and local mean in that region, you have to look at the point along the curve right here. Okay? Along the curve right here. All right, which is what? Along the dish rectangular region that you have right here. See what happened to all those points. It may be the absolute minimum, say somewhere in there, may not be in the middle, may not be the local max or local min. That was the idea. So I'll show you how to take care of the problem. As usual, we start with first partial derivative. Fx is 2x minus 2y, right? X squared derivative 2x, this is 2y. And Fy is negative 2x, right? Negative 2x plus 2. And then what? You set Fx equal to 0, you set Fy to equal to 0, you try to solve for x and y. The first one right here, we have obviously x equal to y. The second one right here, we got x equal to negative 1, 1, positive 1. So together, we have the point x equal to 1 and y equal to 1. There is only one critical value, one critical point, x equal to 1 and y equal to 1. Okay? And we want to see if this is the maximum or the minimum, then a local max, a local mean, we do the second derivative, fxx is equal to, fx right here, fx equal to 2, positive. And fyy, no y in here, so 0. So what? And fxy, fx right here, fxy is negative 2, right? So b is 2 fxx times fyy 0 minus negative 2 squared is equal to negative 4. It's a negative number. So this is neither a local max or local mean. Instead, it's going to be a saddle point. All right. So we do not have any local max and local mean. But we will have some absolute max, absolute mean. It's going to stay on the boundary. So we're going to look at the boundary. Okay? We can skip it, we can erase this because we know that we don't have any local max or local mean. B is negative, right? No local max, local mean. Okay. So let me try to redraw the domain so you guys see it's better. Let's draw it 2D. My x-axis right here, my y-axis right here. Now this time I want you to imagine a little bit more. Think of the z-axis is coming out of the board, okay? The x-axis right here, the y-axis right here. The z-axis coming out of the board. And the surface is somewhere up here, okay? And we have x from 0 to 3, y from 0 to 2. This is your domain. This region right here is your domain. Okay? And then the graph is up here. And you know that there's no local max or local mean in the middle. But you may have some absolute max, absolute mean on the boundary. And we got to take care of the boundary. There are actually 4 line segments on the boundary. This, and that. So we're going to do one at a time. Let's start with this one right here. This line right here. The first line, let's call it L1 then. This line right here, L1, you have what? X equal to 0. That's the line right here. Okay, x equal to 0. And y is somewhere between 0 and 2. This is considered the line segment L1. Okay, y run from 0 to 2, x equals to 0 all the time. Okay, so plug that into your equation. F of x equals 0, right? Y is something between 0 and 2. X is 0. You got what? 2y, right? X 0, this is 0. 2y and y run from 0 and 2. So this thing gonna be somewhere between what? X is 0, this is 0. X is 2.